Good afternoon. My name is Leandria 8. This is Murton and Juan Cardona, and we are CWOD, which stands for Corrective Workout of the Day. And we are doing a weightlifting robot. A basic background of our project, we decided to create a robot that teaches you how to properly weightlift. We understand it is a far-fetched idea in the grand scheme of things, but ideally what we want to do is eliminate how many people in the gym are doing bad lifts. Now, we're not replacing a personal trainer because we're not teaching a workout schematic, or we're not giving them something to go by as far as training regimen. We're just correcting the form when we see it's wrong, or have a robot that we can show as a prototype to show the proper lifts and how to target these lifts properly. A few sponsors for our project. We have Amicus, which is a medical group who offered about $1,200. We have MedEasy, which is also a programming medical software company. And we have Iron Gym, which is in process, as well as Halo. Now, right now, we have about $5,000, and we're looking to get around $3,500 to $4,000 more dollars to cover the rest of our project. Background of our robots. Humanoid robots are robots that have dexterous hands and limbs. So we're looking at our robot to have all two arms and all two legs. With the humanoid robot, it's able to give a person a humanoid feel, or to be able to give you audio feedback and eventually visual feedback. Examples of these humanoid robots would be like the Blade Runner or Terminator, just to give you guys an example of a background.
It's a common misconception that the United States is the only country that lifts weights. It's actually a very popular worldwide thing. So we wanted to make our design very global. We wanted to hit basically everybody that it applies to. We have scores and scores of nations. People don't think of China as a weightlifting country, yet they're one of the best professionally and recreationally. So we wanted to include our entire audience, and one of the ways that we want to do that is by incorporating language. CWOD will be a very visual robot. It'll teach you how to do your weights by showing you visually, physically, but we also have it speaking to you. So our prototype's going to have 3 languages. It'll be English, Spanish, and either French or German. Another aspect that we wanted to include was the units. Because we're dealing with weights, we're only dealing with kilograms and pounds here. But we do want to have it with both. So CWOD will have a unit conversion within itself. It'll be able to switch on the dime. So if you have a pair that's working out together, and one prefers working out in pounds and the other one is more comfortable in kilograms, they can switch back and forth for you. As far as the visual component of CWOD, we already mentioned that it's a very visual robot. So we want to create a very sleek but very neutral design. We want it to be modern. With robots, typically, you have neutral looks. When you get into the humanoid robots, that's where you get a little bit more tricky. So we're just desired a neutral look. As far as our designs go, we had 2 basic options. The first was start from scratch, and the other one is this open source humanoid robot. Starting from scratch is a great idea if you don't have any money. But the unfortunate part of it is that it is highly time consuming. Our project is very much based on programming, so this is not one of the greatest ideas for us because we need as much time as possible for programming. This open source humanoid robot, basically what that is you have manufacturers who produce robots pre-manufactured, and you can purchase these robots completely assembled. You can purchase them just the parts and assemble them yourself, or you can do what we feel is the most efficient option, which is download these parts onto CAD drawings, print them yourselves, and assemble them yourselves.
So as Brian was mentioning, the most important part of our project is the programming. So we don't want to waste too much time on the manufacturing side. That's why going with the open source humanoid robot is a great idea to save time. We would download the SolidWorks files from the open sources and modify the parts as we need, and then we would 3D print them. After we have the 3D printed parts, we will have to purchase other different accessories that we need, like the motors, the actuators, the electronics, the cables, etc. And then once we have that, we will assemble it together, so then we can start programming. After doing research, we came up with 3 different alternative designs. Alternative design 1, as you can see here, is a cost-efficient humanoid robot that after 3D printing and buying all the parts, comes out to $1,000 to $1,500. It lacks human-like features like hands and feet, and it only has 17 joints, which is not ideal because we're looking for a design that has more than 20 joints, so that it can do more movements that we needed to do to teach people how to weight it. Its size is pretty decent. It measures 25 inches in length, and it doesn't have feedback through a screen, only feedback through audio. Alternative design 2 is also very cost efficient. After 3D printing and buying all the parts, it comes out to $2,000 to $2,100. It has 23 joints, which is great. This is what we're looking for, a lot of joints, more degrees of freedom. It lacks effective feedback because it doesn't have a screen or feedback through audio. So alternative design 3 is the design that we're going for. This is an open source humanoid robot. It has 25 degrees of freedom. It measures 33 inches in length. It has human-like representation and enables feedback through the screen on the head and audio. However, it is very pricey. After 3D printing all the parts and purchasing the motors, it comes out to like $7,000 to $8,000. So in this table, we can see all the qualities that we're looking for in the robot, and like the open source, 20 or more joints, human-like features, big in size, screen, audio, and cost efficient. And as you can see, alternative 3 is the design that has most of the qualities. But like I said, it's pricey, but I think we can get the funds to make it happen.
A bit about the programming. So having a background with robot design, we know a little bit about C++ and Java and all these other programs that we could use. However, Python is our most efficient. With Python, we can incorporate position, touch, as well as our actuators that as you see in this Excel file. Well, Python is very easy to learn, especially for newly beginning programmers, as well as it's object-oriented. So because we're dealing with an object, would be a robot, we decided to use Python. Python also with the statements, as C++, you have to do many lines of code just to get one function to run, whereas Python, you can eliminate that into one smaller statement. It also has an interpreter, and which is something that we utilize very well, because if you are to program within Python, the interpreter will allow you to convert it to where the computer can read and also do the lifts for you on one of the softwares.
We're doing something cool. We're designing a robot that has a function that nobody's ever done before. We're essentially starting something new. Because of that, standards are very hard to come by from. As far as our final design, where it could go into the future, we have the IFR, who's sort of been our guide. Basically, they deal with robots that are manufactured industrially. That's where we can go. As far as our prototype, it'll be manual. So at the moment, we still are looking, but there's really nothing that affects our project specifically. As far as the design, we have over 50 parts that we're gonna 3D print. You guys are probably wondering, what are you guys doing? You're engineers and you're just playing Legos over here. What we're gonna do is we plan to make a shell, design, and cover all the wires, the actuators, the servos, all that. We would like to use carbon fiber. We know it's expensive. If not, we're gonna go with a plastic.
So this is the timeline of our project. Right now, we just finished choosing our design. The following steps will be to do CAD simulations, 3D print the parts that we need, purchase all the different electronics, and assemble it together so that then we can start programming.
What's really cool about our project is we have two ways of thinking. The first is, what can we accomplish in 10 months to build a prototype to show in front of you what we can do? And the other one is, where can this go? What are the future advancements of CWOD? And we believe that CWOD can have an enormous impact, and we're really not hyping this up. There's nothing like this. There's a lack of physical trainers in the world. There are people who want to get into weightlifting that don't know how and are hurting themselves. The difference between an efficient and effective workout and injury is a matter of degrees. So our target audience for this project is middle school students, high school students, and any beginner level weightlifters. Our goal for CWOD is to, in the future, have these in high schools, in middle schools, in gyms, teaching beginners how to do it effectively. And in the end, our goal and motivation of this project is to instill a healthy lifestyle. We want to target the younger age groups to make it a cultural thing. And we finished our presentation with our poster, and now we open the floor for questions.
Okay, you said earlier that you were looking at kits, per se. Is this a kit?
It is.
Yeah, it is.
It is a kit. So structurally, it's already designed?
Yes.
Correct.
And so basically what you buy is the CAD or the
They're,
TRL file or SDL files?
they're free, they're open source, you can download them from their website.
Okay, so they've already done all of the conceptual design, CAD drawing, simulation. What are you planning to do?
We're altering the design is the hands. So our manufacturer is called Poppy, and basically these hands are they're just plastic, they don't move at all. What we want is end effectors, so that I can show you grabbing a bar and doing a squat and all this. So we are designing the end effector, and we're also designing a shell to cover all the wires and all that.
Okay, now this is all made out of 3D printed plastic?
Yes.
Polymer.
Okay. What kind of loads can that type of a system handle?
Well, so the first plastic that we saw could only take a load of about 7 pounds. The polymite, it can go up to about 15 to 20 pounds, but ideally what we're using is a lightweight PVC pipe, to give you a visual. And so that would be no more than 5 pounds to carry. It's really just a visual representation of the actual lift.
Okay, and scale-wise, how big is that?
It's 33
Yeah,
inches.
33 inches.
33
And
inches.
8 pounds.
Yes,
It's not designed to be strong because we don't need it to be strong, it's a teaching tool.
right. Because even my background in being in lifting or whatever, just demonstrating lifts, you use a broomstick. And for me, the ratio for my weight for a broomstick is very large. So using a broomstick also, it shows you that even without heavy weights, you still need to be doing the lifts properly. So that's what we're trying to utilize with the robot.
Okay, thank you.
You mentioned something about the standards, and I see that you're going to the robot and the electronic components and all of this. Any standards on the biomechanics or the actual medical portion, right? The bodybuilding side, bodybuilding association worldwide. Are there any standards or something, techniques specifically that you're going to be using in your programming so that you follow exactly how the technique goes and so forth?
ISO mentions, they have like this subgroup that like everything that they don't specifically mention sort of falls into this little category. And I guess that's where CWOD would fall into. Because Poppy is a pre-manufactured thing, the only things that we have to actually look at is the end effectors. The shell itself, we don't have to follow any standards because it's just a skin, it's just covering it. So the end effector is the only thing that we're actually looking at.
But ideally, the background, because and I'll give you my background with certifications, you have to hit a certain angle when you're doing certain lifts. So what we're going to be doing is researching heavily on these different lifts that we're going to control, especially with our prototype, and make sure that the robot itself is doing the actual angle. So eventually, let's say if a person's not hitting those angles, if we have visual detection, it'll be able to see that it's not hitting that angle and then give it the feedback on what it's doing wrong, right or wrong. So definitely we'll take that in consideration because if you're doing it properly, it's in the book. It's a manual lift.
As for future designs of CWOD, we want it to be interactive, we want it to be able to speak to you. We would like to have some sort of visual receptors so it can see what you're doing. There are technologies that we've been looking at that you can put clothes trackers on and it will watch you and it can correct you as you go. As far as our prototype goes, we want to pre-program it on like an Xbox controller and just show you that it has been done, that we're taking the steps to get there.
What microcontroller or microprocessor are you guys using?
You mind if I go back to the slide?
Sure.
Yeah, right there. All right, so we have different. You want to take it? Yeah, we have different ones that we're trying to go in between. Now, all of these are made to where they can function through the Poppy robot. We're just trying to choose which one is actually most cost effective and the one that we can manipulate the most.
Yeah, there's 25 different, 25 actuators that we're going to be using. There's 3 types. They're in the list right there, the 3 first ones. There's 19. The main one that we're going to use is the MX28AT. And then
Majority from down
yeah,
here.
the majority from down there.
And all of these guys are Python compatible.
Yes,
Right.
all of them.
And then in order to go ahead and use some of the different tools that you guys are saying, you have to have the right libraries. Have you guys checked with those microprocessors that you can have the adequate libraries to do your programming?
Yes, they have all the files on the Poppy, on the open source Poppy. They have all the files and even the RTMs, everything for you to be able to see the compatibility. So before we even utilize these different motors, we make sure it was compatible and that we would be able to use it.
Now, the other thing is that this robot was not designed to do weightlifting or any kind of those movements. Are you guys taking that into account when it comes into maybe doing some lifts or certain, I mean, the center of mass is going to go ahead and shift
Yes.
while doing certain
Um,
movements?
as far as when we're simulating weight lifts, we're only going to use a PVC pipe or like a styrofoam pipe. It doesn't have to be anything special. Yes, that's going to affect it. That's all going to be pre-programmed.
The thing is, at the end of the day, you don't want your robot to go flat face. So just make sure you have something in the back
Okay.
comfortable.
Thank you.
Any comments? Dr. Cunningham? Great. Thank you very much.